Hello my fellow developers, let's talk about distributed PostgreSQL. And this might sound confusing to some of you. Why? Because what do we know about Postgres? Postgres is a database that was designed for single server deployments. But there are certainly times when you want to make it scalable, when you want to make it distributed. And that's probably why you're watching this video right now. And that's the question, how can we make a single server database instance truly distributed, truly scalable? But remember, my friend, that we are talking about Postgres, and Postgres has a very rich ecosystem of extensions and other solutions. And in that ecosystem, you can literally find a solution for pretty much every technical challenge. And distributed PostgreSQL is not an exception. The ecosystem is here to help us. Today we are going to review 3 solutions that can fall in the category of distributed Postgres. We will start with a multi-master asynchronous replication between standalone Postgres instances. Next, we will review the multi-master sharded Postgres cluster when you shard your database across multiple standalone Postgres servers. And finally, we will talk about multi-master shared nothing architecture. There are distributed SQL databases that run on PostgreSQL and they turn Postgres in a truly distributed solution. So let's not waste a minute and do a deep dive. Before we review those 3 solutions that make Postgres distributed, I want us to step back and understand why would you want to have distributed Postgres in the first place. Coincidentally, there are also 3 primary reasons for that. And let's start with the first one, which is high availability or resiliency. How about we take this simple example? Let's say you deployed Postgres in a cloud environment and right now it's running happily in availability zone number 1. And then suddenly a few days later this availability zone goes down and it brings down your database. Your database is unavailable and your applications that were connected to this database instance also experience the same outage. That's one of the reasons why you want to have a distributed PostgreSQL, because if you have multiple Postgres instances running across 3 availability zones, let this one be availability zone 3, availability zone 2, and availability zone 1. Then let's say if you have an outage in the availability zone number 2, this Postgres instance goes down, but the remaining 2, they are alive and they can continue serving your application request. And this is what you can achieve with distributed Postgres. That's reason number 1, high availability and resiliency. The second reason for having distributed Postgres is scalability. You want to scale your data and you want to scale your read and write requests. Let's take another example. That's my Postgres instance. It still runs in some cloud environment. It gets all the data from the application as well as read and write requests. At some point, I outgrow the storage and compute capacity of this database server, and I need to scale. How do we scale with databases that are designed for single server deployments? Right. We use the vertical scalability. It means that you would provision a database server with more CPUs and with larger storage space, and then you would migrate from this database instance to the following one. And after that, you will be able to handle even more traffic and even much more data. However, if your application is still live, if you're getting more users, if you're growing, then at some point in time you have to repeat this process. You would need to provision a database server with even more resources, and then you would need to transition to this database server. You would need to migrate, and after that you will be able to handle even much more data and much more traffic. However, there is a problem with this vertical scalability approach. The first one is that this migration between database servers usually takes downtimes. Your application will not be available while you're migrating from one database server to another. But that's one thing. Another thing is that at some point in time, you will not be able to find a database server that will be able to handle your application workloads, or the database server can cost prohibitively high. And that's exactly why many want to have distributed Postgres that can scale reads, writes, and data across multiple Postgres instances, because with that you will be able to scale using commodity hardware. Let's say these 3 Postgres database instances are no longer enough, you can add 2 more, or you can add as many as you want to your fleet, right? So that's the second reason for having distributed Postgres. You want Postgres that can scale easily. And the final reason for having distributed Postgres is geo distribution. If you have a geo distributed Postgres, then you can comply with data regulatory requirements by storing user data in specific geographies. And second, you can handle user requests with low latency no matter where the users live. So let's take the final example with the focus on the low latency. Let's say that your application, your service operates in the United States, European Union, and Asia. Presently, your database is deployed in the United States. So what does it mean from the user experience? What does it mean from the latency standpoint? It means that all your users who live in the United States, they will have the best experience because their requests will be processed with the lowest latency possible because the database is also deployed in the United States. The users who live in Europe, they will have a little bit poor experience because it will take much more time for their request to travel to the United States to get the data from the database because that's the higher latency. And the user experience will be even worse for those who live in Asia because their requests have to travel through the land under the ocean before they get to the database that is deployed in the United States. And if you have a geo-distributed Postgres, then what can you do? You have the same countries, and then you deploy your Postgres instances in all of those countries, and you store user-specific information in those geographies, and the users from the United States work with the data in the United States, the users from Europe read the data and write the data in the European data centers, and the same applies to the users in Asia. So that's the geo-distribution in action, and for that you want to have distributed Postgres as well. Alright, my friend, now you understand why would you want to have distributed Postgres. And now, let's review those solutions that make Postgres distributed. The first solution that can come to mind when you think distributed Postgres is a multi-master deployment with the asynchronous replication. Postgres does support the asynchronous replication out of the box, but as of Postgres 16, it still was not advised to use this replication for multi-master configurations. That's why today we will break down this deployment option by using the EDB distributed, one of the solutions that is provided by a third-party vendor. Let's take a look. How about we review this sample configuration? I'm running my multi-master deployment in some region A across 3 availability zones: Zone A, Zone B, Zone C. Alright? And the multi-master configuration assumes that you have several primary instances of Postgres. And that's what I've done. I have the primary instance in Zone A, another primary instance in Zone B, and also an instance in Zone C. Okay? Now the application can connect to any of those instances and execute not only read, but also write requests. If you're using the EDB distributed, then they also suggest you considering the PGD proxy component that acts as a proxy between your client and your database instance. Why is it useful? Imagine that you have several primary instances deployed in the same availability zone, and the PGD proxy will decide what instance needs to handle your user requests. Okay. This client application is connected to this PGD proxy, and the PGD proxy routes the traffic to this primary instance. But the same client application can connect to another primary instance Postgres in another availability zone. And in this case, it can start writing and updating data in all of those locations, which means that then those primary instances, they need to replicate changes introduced by this client application or by other applications that can be in your deployment. And as long as we are using asynchronous replication, there is an asynchronous application process running between instances of availability zone A and B. And also you have this asynchronous replication between zone C and zone A and between zone C and zone B. Another question is, why would I want to have these standby instances attached to every primary instance? You do this from the high availability perspective, because let's say if this primary instance goes down, right, something happens, then you don't want to lose the data that was stored on this instance. And that's why one of these standbys can be promoted to the primary, and then it will start handling the user traffic. Why do I have 2 standbys? When it comes to the copy of the data stored on a particular primary instance, you want to have synchronous replication. And if you're using the synchronous replication of Postgres, then you need to have at least 2 standbys. If you have just 1 standby, then if that standby goes down, then you will not be able to process writes on your primary instance. You will be stuck because you no longer have any standbys. That's why you want to have 2 standbys for the synchronous replication. Okay? So next, this solution looks reasonable, but what are the trade-offs? Let's discuss at least a few. The first one is data lag. You have this asynchronous replication that sends changes between the primaries deployed across several availability zones. And let's take this example. This client application updates something in this primary, like record number 1. And then you have another client application that wants to read this record from the second primary. And this update is to be replicated from this primary to another one. Until this happens, this instance of the application will be seeing another value for the same record. So be ready for some data lag, be ready for some data staleness. And another issue that is related to the asynchronous replication is the conflict resolution. So let's take an example with the same two application instances. So this client application updated one record setting value to 1, but this application also updates the same record setting the value to 2. And then they will be replicating this change between each other. And which one wins? Should we use 1 or 2? And what should we use if those were written at the same time? You would need to deal with this, and you would need to deal with conflicts a lot, especially if you're dealing with write-intensive workloads. Alright, those are a few trade-offs that you need to keep in mind if you use a multi-master deployment with asynchronous replication. But enough of it. Let's get to the second solution that can make your Postgres distributed. The second option is a sharded Postgres cluster with a coordinator. Let's take a look at another example. I'm still going to run my solution in a cloud region A across 3 availability zones on A, B, and C. And the sharding assumes that you take your database data and split into shards, and then those shards are distributed evenly across your Postgres instances. This is exactly what happened in my example. I have the shard 1 and 5 from shard 1 through 5, and those shards are stored on this primary instance of Postgres. Then I have shards from 6 through 10, and those shards are located on this Postgres instance. And the remaining shards from 11 through 15 are located on this instance of Postgres. And by distributing the shards, you are distributing your data, and also you are distributing and scaling your read and write workloads. That's one of the biggest advantages of the sharding. However, there is one important thing to keep in mind. All these primary instances of Postgres, they are independent. They don't know anything about each other. They don't communicate to each other. That's why you need to have a special component called coordinator. So in this example, I'm talking about Citus Data. Citus Data is one of the extensions for Postgres that makes sharding possible. And in Citus, you need to have this coordinator. Your client application connects to this coordinator, and then coordinator decides what database nodes will be executing this specific client request. Some of the client requests will be mapped to one of the primary instances. Some of the client requests have to be executed across the entire cluster of your database nodes. All right, so keep this in mind. You need to have this coordinator. You also need to have standbys and asynchronous replication, ideally, for every primary instance in your deployment. Because if this primary instance goes down, you don't want to lose the data, and that data will be stored on those standby instances. And then you do the same, you deploy standbys for every primary you have. Okay. Next, what are the trade-offs? Let's clean all these drawings and discuss the trade-offs. So one of the obvious trade-offs is the coordinator. These primary instances of Postgres don't talk to each other, which means that all your application instances, they communicate to the cluster through this coordinator. And this coordinator is your single point of failure and your bottleneck. You need to keep an eye on it, and you need to make sure that you're running several instances of this coordinator, and that coordinator has enough of CPUs to handle all of your application requests. Another trade-off is related to distributed transactions. Transactions that span several shards and database nodes. Let's take another example. My client connects to the coordinator, and then it asks coordinator to update 2 records. One record is stored on the following primary instance, and another record is stored here. So presently both records has the value of 0, 0 here and 0 there. What the client wants to do, it wants to update the first record from 0 to 1 and the second record from 0 to 2. This request went to the coordinator, and the coordinator starts this distributed transaction, and then shortly the first record has been committed and updated. updated, so that's the current value right now, 1. However, the second record has not been updated yet. And while we have this situation, there is another application instance, and this application instance also connects to this coordinator, and that wants to read the values for these 2 records back. It reads the first record, and the coordinator returns 1, right? And then it reads the second record, but 2 has not been committed yet. That's why you are getting 0 back to this application instance. And that situation is known as stale reads. So keep this in mind when you're dealing with distributed transactions. Alright, sharded Postgres is one of the solutions for making Postgres distributed. And how about the last one? Let's review it. The last but not least is a distributed shared nothing database. In the Postgres ecosystem, we have YugabyteDB. YugabyteDB is a distributed SQL database that runs on Postgres, and it also makes Postgres distributed. Let's take a look at our final example. Same as before, I keep running my solution in the region A of some cloud environment across 3 availability zones, zone A, B, and C. I have a 3-node YugabyteDB cluster, and those nodes are deployed across those availability zones. Node 1 is here, node 2 is in zone B, and node 3 is in zone C. Similarly to the sharding solution that we discussed for Postgres previously, YugabyteDB also shards your data across all of those nodes. This way you can scale your data and you can scale your read and write workloads. But unlike the classical sharding solutions, you don't see any coordinator here. Why so that? Because YugabyteDB nodes, they are aware of each other. They talk to each other. They send heartbeats to each other, and that allows them to distribute data evenly on their own, and your application can connect to any of these nodes, run any distributed transactions, and the database transparently will execute this transaction for you. Also, if any of these nodes goes down, you're not losing any data and you still remain available. Why? The other 2 nodes, they will be keeping a replica copy of the data that was owned by node 1 previously, and they will take all of the client requests that were first dedicated to node number 1. So you will be available, you will be up and running, right? That's how you can make Postgres distributed on Yugabyte. Finally, what's about trade-offs? Because we discussed trade-offs for all the solutions. Let's clean our drawings first. One of the trade-offs is related to extensions that were created for the Postgres storage layer. YugabyteDB has its own storage architecture. YugabyteDB uses Postgres in its query layer, and its query layer is literally Postgres itself, but the storage layer is what makes YugabyteDB different. This is how YugabyteDB supports ref-based synchronization, distributed transaction, automatic sharding, and load balancing. And that's why those extensions are no longer needed with YugabyteDB. But at the same time, you no longer have any problems with vacuum and transaction wraparound issue. Okay? That's YugabyteDB, another option for making Postgres distributed. How do you like this, my friend? Even though Postgres is designed as a database for single server deployments, its ecosystem is so rich that you have several options for making it distributed. So pick an option that works best for you and start building scalable and fault-tolerant applications running on a distributed version of Postgres. And keep mastering databases. See you soon. Bye bye now.